Hi, what we're going to do today is we're actually going to do some investigations on quite a viscous solution. So what we're going to do is we're going to take a sodium silicate solution which has about 10,000 to 15,000 centipoise viscosity. We're going to put in to the Chemisense calorimetry reactor about 10 mils. The reason we can get away with 10 mils is, though this reactor has a volume of 250 mils, you only need 10 mils to cover the thermocouple in the base of this reactor. And because we're sort of dealing with a viscous system today, we're actually using this kind of stirrer as maybe opposed to this type of stirrer or any of the other stirrers in the range. So in summary, today we're going to do some investigations on a viscous solution. We're only going to use about 10 mils. We could use, 50 mils, 100 mils, 150 mils. As I say, the volume of this is actually 250 mils. So we've got about 10 mils there. To say one thing about the lid, I'm just going to turn this into this angle. It's really quite sweet because then this will actually then just slide down, and then we're just going to put the 4 bolts. Okay, so I've installed the lid, and I can just kind of hand turn the shaft now, and it just turns nicely, no clashes, and you can see the way that the shaft cleverly kind of misses those internal probes, so that's pretty cool. So the next thing to do is just to put the handles on so we can lift the calorimeter in and out of the isothermal bath. Okay, so the next thing I'm going to do is take the reactor. I'm going to sort of lift it up by the handles and then place it into the CPA202 isothermal bath. It's kind of worth noting that this bath is partly why the reactor is actually so accurate or precise, because really the whole calorimeter is really isolated from the sort of ambient conditions because it's sat permanently within this bath, and we can you get a very nice view through this window once we turn it on, because there'll be a light which will kind of show us what's going on in the calorimeter as well. So as I say, let's get the calorimeter into there. So you can see we've dropped it down, and actually the majority of the lid, as you can see, is covered by the insulating or thermally insulating solution, so it's really good because unlike a lot of calorimeters where you just know that you're getting heat exchange through the lid, because the lid is often not jacketed, this one's very different. Okay, so coming out of the lid we actually have obviously kind of 3 connectors. We're not going to use this one today. This is the validation heater. You absolutely do not need to calibrate ever the CPA202 calorimeter. It's factory calibrated, but people do want to validate that calibration on occasion. So this one has been set up with an internal heater. I'm not going to use it today, but we call it really the validation heater. Allows you to put in a no amount of power and obviously see the kind of correct response to that power. I'm not going to use it today. We normally would actually take it out of the reactor, but it just happens to be in there. The calorimeter actually has a heat pump as part of its temperature control. So we'll be connecting the heat pump, and then we'll also be connecting the internal temperature thermocouple as well through here. Okay, excellent. Okay, so as standard we have 2 types of ways of coupling the stirrer motor to the stirrer in the reactor, magnetic or just sort of direct mechanical coupling. So I have 2 shafts, and in this one I'm going to use the longer one. The longer one is the direct coupling and the shorter one is for the magnetic coupling, so I'm going to use the longer guy today and use that. Then I'll basically place that between the top of the stirrer here and then couple that up to the motor here. It's worth noting that even when it's stirring, we're obviously very thermally well isolated, being within this sort of extra external bath, but the viewing window really does give you a nice view into the calorimeter, so you can sort of still see what's going on in there. There's quite an intense light that's actually quite useful for seeing in there. Hi, with the CPA202 calorimeter, there's actually 2 pieces of software come with it. You get the kind of chemical control system, and you also get a reporting piece of software. You can kind of see your data, see all the different various channels that come with it. So there's a reporting software, and there's also the chemical software for controlling the calorimeter as well. So you have kind of 2 main windows. You have real time and you have Profinder. So real time just kind of very quickly allows you to see what the calorimeter is effectively doing in real time, and you can do things like you can set the stir speed, you can set the power on a validation heater if you so wished, you can set the temperature control and tell it to go to that particular temperature. But we also have a piece of software called Profinder, which allows you to write a sequence of events, in a process and run an experiment. So I've written one previously here. I have a start and I have an end, and in it I have go to temperature, meet some conditions, scan to a new temperature, meet some conditions, scan to a new temperature, meet some conditions. So what I'll just do is so what I have here then is I have a start and a beginning, and what I'll do is I'll start the log, I'll call my experiment EXP1 operator, MP. And then I'm going to tell the experiment actually what to do. So what I will do is, I shall say go to new temperature. And what will that new temperature be? That new temperature will be 25 degrees C, for example. So start experiment, go to 25 degrees Celsius. Then I'm going to basically tell it to stay at 25 degrees Celsius until some conditions are met. So let's edit those conditions. So what I'll say is do a signal stability on the reactor temperature 200, 200. So there has to be a certain amount of stability on the temperature for this condition to be met. So now I have a condition, so start, go to temperature, be stable, and when you are stable then that condition is met. And now I'm going to tell it to scan up in temperature. So we'll tell it to go up 1 Kelvin per minute up to about 35 degrees. And then I will put another condition in. There's lots of ways of doing this. This is kind of a very simple way of doing it, but there is much more complexity, not complexity, much more sophistication if you so wish it as well. I'm just kind of giving you a quick insight as to how you can just really drag and drop, change some parameters, and you can really write really quite sophisticated experiments, obviously, using this. So, start experiment, go to 25 degrees C, meet some conditions, scan up to 35 degrees, meet some conditions, and then let's scan again. And now we will do some more conditions. And then the last one we will go to scanning temperature. Go to 60. Have some conditions. Whoops, reactor temperature 200. Last one 200. And that's it. This should now really be a sequence of start experiment, go to 25 degrees, meet some stability conditions in terms of temperature, go to 35, meet some stability conditions in terms of temperature, go to 45, meet some stability conditions in terms of temperature. That one here, I just need to put that in, 1, and go to 60. And then meet some conditions. Now what will happen, I have some previous data there, so here, so I will just go to so this is our software, and I've previously done this, and I'll just zoom in on where I actually did this, and you can see that I put in a series of conditions, and the reactor temperature basically followed what I was requesting it to do as well. Okay, so it's quite simple. We have an intuitive real-time window where you can just sort of see what it's doing in real time. and then you can write quite a nice series of events. It can be quite sophisticated in terms of what you do. I just wrote a simple one where it was scanning temperature. And it's worth knowing that even though we're scanning temperature, so we're not isothermal, we're kind of adiabatic, we're still able to get real enthalpy data in real time. And it doesn't matter anything about the viscosity of the solution, the data is valid, and if the area changed because we were pumping in, the data is still valid and you get real-time calorimetry data. Okay, thanks very much.